Welcome to the 𝑊 Academy. My name is Amisha Classo, and in today's video we will continue with the chapter Thermodynamics, class 11, chapter 5. Now in today's video we will learn about some of the applications. Now many chemical reactions, they involve the generation of gases that are capable of doing some kind of mechanical work or even some kind of generation of heat. Now it is important for us to quantify these changes and relate them, that how these changes are associated with the internal energy. So now first application, let's begin with understanding the work that is being done. So first of all, let us concentrate on the nature of the work a system can do. We will consider only the mechanical work, that is the pressure volume work. So in this case we are considering a type of mechanical work in which we are taking pressure volume work. So we will understand how pressure and volume are have a relation between them. So for understanding pressure volume work, let us consider a cylinder which contains say 1 mole of an ideal gas that is fitted with a frictionless piston. Total volume of the gas is say Vi, that is volume at the initial stage, and pressure of the gas is say P. If external pressure is Pex, which is greater than that of P, piston is moved inward till the pressure inside becomes equals to Pex. So now what we are saying is that we have a closed cylinder in which we have 1 mole of an ideal gas that is filled. Okay, its initial volume we are saying it is Vi, and we have the pressure inside as P. Now we are considering if the pressure outside is equal to Pex, and if we say that this pressure outside is greater than that the pressure inside, we are going to push this piston inside so that our pressure becomes equal to that of the outside, that is the external pressure. So let this change be achieved in a single step and the final volume be Vf. So now what we have done, we have exerted some pressure and the volume has reduced, and we have the final volume, that is Vf. Now during this compression, suppose piston moves a distance L and its cross-sectional area of the piston is say. Now what we are considering, this piston is moving with a distance say L, okay, and its cross-sectional area of this is say A. Then the volume can be written as, or the volume change can be given as, the distance travelled into the area or the cross-sectional area. So that can be written as delta V equals to Vf minus Vi, that is the change in volume that happens. So we have the final volume minus the initial volume. We also know that pressure equals to force upon area. So if we rearrange this formula, wherein we know the force on the piston, if we have, so we take this area over here and we derive the formula for force. So in that case, so what we are doing here, we are rearranging this formula, we take this one here, so we'll get force equals to pressure into area. Therefore then we can say that the force on the piston will be equal to, that is the external pressure into the area. Now if W is the work done on the system by the movement of the piston, then we can say W will be equal to force into the distance. Now force, we already know that it is P external into the cross-sectional area, and distance we know is L. So substituting all of this, we can say that P external. Now here what we are doing is we are taking A into L. If we see here, we had taken as delta V, that is the volume change. So that same thing we are substituting here. So since A into L equals to delta V, we can substitute that over here. Then we have minus P external delta V. So this, if we open up this delta V, will get Vf minus Vi. So now the negative sign, if you see there is a negative sign here, the negative sign of this expression, it is required to obtain the conventional sign for work, which will be positive, okay. That will indicate that the compression work is done on the system. So what we are saying is that this negative sign, we want the final equation to have a positive sign. So if we take a negative sign now here, this will follow the convention and we will at the end get a positive sign, that we will see how later. okay, and also that will indicate that the compression work that is there, it is being done on the system. So therefore the sign is positive. Now here, because we have, now how this negative will change to positive. So here if you see, the final volume is what, it is going to be less because the pressure is exerted and therefore the volume has reduced at some extent, and the initial volume which is there, it is going to be higher than the final volume. So here if you see, we will have a negative sign because this value is going to be greater. So if this value is greater, then we will have a negative sign over here. Now if you have minus P external into minus delta V, so this minus and this minus will become positive, and P external delta V will be a positive value. So therefore we can say that the compression work is done on the system. Now if the pressure is not constant at every stage of compression but changes in number of finite steps, then the work done on the gas will be summed up over all the steps and will be equal to minus summation of P delta V. Now what they are saying is that if the pressure, say, is not constant, okay, it keeps on changing at different steps that are taken at or finite number of steps, it keeps on changing, then what we can say that the work that is being done on the gas, it will be summed up of all the steps, as in we are going to sum up all the finite steps that are happening, all the change in the pressure, we are going to add it, and therefore we will get minus summation of P delta V. Now if the pressure is not constant but it changes during the process such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression the volume will decrease by an infinitesimal amount, that is delta V. Now they are saying if, say, the pressure is not constant again but it is changing in very smaller steps, okay, in that case what we can say that there will be a change in the volume as well, but this change is going to be very small, that is delta V. In such a case what we can do is that we can calculate the work done on the gas by a relation, that is W equals to minus integral of Vi and Vf Pex dV. Now here Pex at each stage will be equal to what? P internal plus the change in pressure that occurs. In case of compression, so in an expansion process under similar conditions, the external pressure is always less than the pressure of the system, that is Pex will be equal to P internal, that is the pressure inside, minus the dP, that is the change in pressure that occurs. In general case, we can write that P external will be equal to P internal plus or minus the change that occurs. Now such processes are called as reversible process. So now here what they are saying is that if the pressure is not constant and there is some kind of change that is happening, so if Px equals to, we are saying that it is depending on the P internal, that is the internal pressure plus the change that occurs, the small change in pressure that occurs. So this, if we consider, we can say that P external can be equal to P internal. Why? Because what we did initially, the pressure outside was greater than the pressure inside. So we reduced the inside pressure so as to match the pressure on the outside, that is to match the external pressure. So now if we are saying that it is not constant, as in both of the pressures are varying, then what we can say that P external equals to P internal pressure with a difference of plus or minus of dP, that is a very slight change in pressure. So such processes, they are called as reversible process. So a process or change is said to be reversible if the change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that the state and the surrounding are always in near equilibrium with each other. So now reversible process, it is being said that it has some kind of change that is occurring, but these changes are so small that they can be reversed back. They are not like huge that you cannot take a step back. They are infinitesimally small and therefore they are very close to the equilibrium state, as in they are like very near to the equilibrium state. They might not always be at the equilibrium, but they will be in and around the equilibrium of the state. So now processes other than the irreversible processes, they become the processes other than the reversible processes, they become the irreversible process. Now in chemistry we face a problem that can be solved if we relate the work term to the internal pressure of the system. So now we are going to see how we can relate the internal pressure, that is delta P In of the system to the work. We can relate work to internal pressure of the system under reversible conditions by writing the equation. So WREV is reversible work equals to minus integral of external pressure dV equals to this. If you substitute now, we have said P external is given by P internal plus or minus the dP. So that if you write, then we know that dP into dV is a very small change, okay, and therefore we can integrate it and write it as W reversible equals to minus integral of P In dV, okay. Now the pressure of the gas, that is P internal, which we can write as P now, can be expressed in terms of volume through gas equation. So we know that for n mole of gas, of an ideal gas, we can write PV equals to nRT. So now we are using the ideal gas equation. Therefore at constant temperature, that is isothermal, we can substitute the P that is there. So here what we have done now, since this is removed, that delta P factor is removed, this internal pressure which is there, we have related to it as the pressure of the gas itself. Now if you relate this as the pressure as the gas itself, then for an ideal equation we know that PV equals to what? nRT upon V. So now if we substitute this P in the above equation, we will get nRT dV upon V, which equals to, finally removing the integral sign and removing the log, we get minus 2.303 nRT log of the final volume upon the initial volume. Now what is this free expansion? So expansion of a gas in vacuum where its external pressure is 0, that is known as a free expansion. So whenever the expansion is happening of a gas in vacuum wherein the external pressure of the system is 0, it is called as a free expansion. Now work is done during free expansion of an ideal gas whether the process is reversible or irreversible. So now in such a case they are saying that for free expansion there is no work done. Doesn't matter if the process that is occurring is reversible or irreversible. In both of the scenarios no work will be done. Now we can write the equation 5.1, that was what? Delta U equals to Q plus W. Okay, this was the internal energy equation that we had. So if we substitute now here the work that is being given here, delta U equals to Q minus P external delta V. Now if the process is carried out at constant volume, that is delta V if you consider 0, if this you consider to be 0, then this whole term becomes equal to 0. So internal pressure internal energy will only depend on the Q that is written here. Now isothermal and free expansion of an ideal gas. So for isothermal, where we say temperature is constant, expansion of an ideal gas into vacuum, that is W will be equal to 0, since P of Ex, that is pressure external, is also 0. Also Joule determined experimentally that Q is 0, therefore if Q is 0 then U is going to be also 0. So in a equation, delta U plus Q plus W can be expressed for isothermal, irreversible and reversible changes as follows. For isothermal reversible change, we can write Q equals to minus W. So we will write it as P external Vf minus Vi. This we already know because this minus and this whole term becomes minus. So we get a positive value. For isothermally irreversible change, we know minus W will be equal to nRT ln of Vf upon Vi sorry, which will be equal to 2.303 nRT log of Vf upon Vi. And for adiabatic change, we know Q equals to Q will be equal to 0. Therefore, delta U will be equal to work done, that is for adiabatic change. So this was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.